Alright, let's work on some absolute value graphs and their equations. The graph of y equals absolute value of x looks like this. It's a v centered on the origin with a slope of 1 and -1, symmetrical on the y-axis. So what we're going to do is use function notation and recognize the transformations and its effect on the equation and the graph. So if we have f of x equals radical x, then what would happen if we had f of negative x? Well, that's asking me to plug in negative x for x, so we have the absolute value of negative x. Now we know that f of negative x, using function notation, is asking me to negate the x values, which means we have a reflection over the y-axis. So the graph of y equals the absolute value of x will yield the graph of y equals the negative absolute value, the absolute value of negative x, yielding the same graph because it's symmetrical over the y-axis. If we have f of x equals absolute value of x again, what would happen if we had negative f of x? Well, that's just asking me to put a negative in front of my function. Using function notation, I should be able to recognize that this is asking me to negate my y values, which means I have a reflection over the x-axis. The graph of y equals the absolute value of x looks like this. So that means the graph of y equals negative absolute value of x will be its image after a reflection over the x-axis, negative absolute value of x. Let's take a look at what happens for the inverse function. If we have f of x equals absolute value of x, what would the inverse graph look like? F inverse of x. Well, let's just do a little side work. We have y equals the absolute value of x, interchange x and y, x equals the absolute value of y. So now this is a problem because I can't solve for y here. I don't have a tool to get rid of these absolute value bars. When we worked with quadratics, the inverse of a quadratic was taking the square root. In this case, I don't have a tool to get rid of this. So I can't call this f inverse of x equals, because it's no longer a function of x, it's a function of y. So the inverse graph I have to express for now until we learn another way to express this. I can say that the inverse is x equals the absolute value of y. Well, fortunately, I know that the image of a function and its inverse is a reflection over the line y equals x. So let's see what the shape of this graph would look like just by our knowledge of reflecting over the line y equals x. Here is the graph of y equals the absolute value of x. If I wanted to find the inverse of this graph, I would reflect over this line. That's the line y equals x. So the line y equals x is on part of the absolute value graph. So that's going to be its own image. And then this line will simply fold over there. So this is what the graph of x equals the absolute value of y looks like, which is the inverse graph of y equals absolute value of x. Now we'll work on some translations. F of x equals the absolute value of x. What would happen if we had f of x minus 3? Well, that's just asking me to go to my function f and plug in x minus 3. So, the absolute value of x minus 3. So now, using function notation, I should be familiar with this. This is a horizontal translation of positive 3 in an x direction and 0 in a y direction. So now I should be able to recognize from the equation that this is changing in an x direction, but it's moving right 3 units because it's inside of the function. Again, the difference between inside the function and outside the function is whatever the function is calling for you to do to the x term. In this case, the function is calling for me to take the absolute value of something. So inside of the function means I'm subtracting 3 before I take the absolute value of something inside of the function, where this function is taking the absolute value of something. So here is the graph of the absolute value of x, which means I know the graph of y equals absolute value of x minus 3 is going to move to the right 3 units. So this vertex will now be right here, if that's 3. So here is the graph of y equals the absolute value of x minus 3. Inside of the function, opposite sign. Well, what if we had f of x equals the absolute value of x? What would the graph look like if we were to subtract 3 after the function? Well, that would be the absolute value of x minus 3. So this is outside of the function, function being taking the absolute value of something. So this is saying I'm taking the absolute value and then I'm subtracting 3, which means I am moving in a vertical direction down 3 units. So here's the graph of y equals the absolute value of x, which means the graph of y equals the absolute value of x minus 3 looks like that. So now we're not only familiar with using function notation to recognize the translation, we're also familiar with the equation and its effect on the graph, and conversely, the graph and its effect on the equation. Let's work on some dilations. What would happen if we had a dilating factor of 3? That's asking me to multiply my function by 3, so 3 times the absolute value of x. Here is y equals the absolute value of x. So we're multiplying by 3, which means we're multiplying all of our y values by 3, which will make the graph more narrow. So this is the graph of y equals 3 times the absolute value of x. So multiply by a fraction. Absolute value of x. What would happen if we had 1/4 times f of x, which is 1/4 times the absolute value of x. The absolute value graph looks like this. And if we're multiplying by a fraction, it's going to make the graph more wide. Let's just pretend that's symmetrical over the y-axis. This is y equals 1/4 times the absolute value of x.